For as long as we have looked into the night sky, we have tried to measure the universe by one simple idea: distance. We measure time to organize our lives. We measure distance to locate things. And we measure light because it carries information across both. Our clocks have become extraordinarily precise. Yet precision does not necessarily mean that we have identified the deepest quantity being measured. When two objects are separated, we naturally assume that the separation itself determines how strongly they can influence one another. Light seems to confirm this picture. The farther we look into space, the farther back in time we see. The universe appears to us as an archive written in photons. But what if distance is not the fundamental quantity? What if what really matters is not how far apart two systems are, but how strongly they are coupled? To investigate that question, we do not need to begin with a galaxy. We can begin with something much smaller and much more controllable. A laser gives us a remarkably precise source of electromagnetic radiation. Its wavelength, direction, and intensity can all be controlled. We send that light into an optical system designed to produce a very specific electromagnetic phenomenon. Under the right conditions, the light undergoes total internal reflection. But the story does not end exactly at the surface. An electromagnetic field extends beyond the interface. It does not propagate into the second medium like an ordinary beam. Instead, it decays rapidly with distance. This is the evanescent field. It is invisible to the naked eye, but its physical consequences can be measured. Its amplitude can be described, in the appropriate regime, by an exponential dependence. E of z is proportional to e to the power of negative kappa z. Move farther from the surface, and the field falls away. Now imagine bringing a second optical element into that fading field. The distance between the two surfaces becomes a precisely controllable experimental variable. If the second system enters the evanescent field, it can interact with the electromagnetic energy surrounding the first. The two systems become optically coupled. Increase the separation, and the coupling weakens. Reduce it, and the interaction becomes stronger. At first glance, everything seems to depend simply on distance. So we plot the measured coupling against distance. We obtain a rapidly falling curve, and it is tempting to stop there. But change the angle, change the wavelength, change the optical geometry. Suddenly, the curves are no longer identical. Perhaps distance alone is not the right variable. Instead, we can combine the relevant optical quantities into a dimensionless parameter. We define x equals 2 kappa d. Now distance is no longer considered in isolation. It is combined with the physical parameters that determine how rapidly the evanescent field decays. This leads to a testable hypothesis. Perhaps the coupling can be described by a common mathematical form. C equals the exponential of negative ax to the power q. But a good curve fit is not a new law of nature. Almost any sufficiently flexible model can reproduce data. The real question is whether the model can predict measurements it has never seen. And this is where our broader theoretical question enters. A DCCM-type model can be written in the form C equals the exponential of negative v over v sub c, all raised to the power n. Could the exponent hidden inside the optical data be related to this deeper coupling law? It is an intriguing possibility. But science becomes interesting precisely where intuition stops being enough. We have to determine whether the exponent we measure has a unique physical meaning. Suppose the quantity v over v sub c itself scales with our optical variable as a x to the power p. Then the equation becomes c equals the exponential of negative ax to the power q, where q equals pn. And here is the crucial limitation. Optical measurements can reveal the combined exponent q. They cannot, by themselves, tell us how much of that exponent belongs to p and how much belongs to n. So instead of making the claim larger, we make the experiment stronger. We build a system in which every important variable can be controlled and measured independently. The separation is adjusted with nanometer scale precision. Every movement becomes a measured quantity rather than an assumption. We repeat the measurement at different angles. 42 degrees, 45, 50, and 55. At every position, the detector records the optical response. Thousands of measurements begin to form a map of the coupling behavior. The data are not perfect. Real measurements contain noise, fluctuations, uncertainty, and systematic effects. Distance measurements have uncertainty. Angular measurements have uncertainty. Even the detector itself introduces noise. A credible model must survive all of it. We now allow the generalized coupling model to learn only from the calibration data. It estimates two parameters, A and Q. And then we do something important. We lock them. No adjustment, no additional fitting, no second chance. Two new angles are hidden from the model, 60 degrees and 62 degrees. Some distances are hidden as well. The model must now predict the unseen measurements using only what it learned from the original experiment. And now we reveal the hidden data. Some points approach the predicted curve. Others begin to separate from it. These differences are not automatically a failure. The question is whether they are consistent with measurement uncertainty, or whether they reveal a systematic limitation in the model. So we do not trust a single simulated experiment. We repeat the entire procedure thousands of times. 5,000 trials. 5,000 different realizations of experimental uncertainty. Instead of one answer, we obtain a distribution. We can now ask how stable the inferred parameters are. and how often the model succeeds when confronted with unseen data. But there is another question. Does the generalized coupling law actually explain the data and the complete optical model from which the measurements arise? We compare the models using predictive performance and statistical evidence, not because statistics can tell us what nature is, but because they can tell us when a model has failed to predict what it promised. At this point, we can separate the evidence into layers. Optical coupling is measurable. A universal scaling law is testable. And the connection to DCCM remains a deeper question. We cannot honestly say that DCCM has been proven by this experiment. Not yet. And perhaps the most important part of science is knowing exactly where the evidence ends. But the question that motivated the experiment has not disappeared. It has simply become more precise. Is physical separation the fundamental quantity? Or is distance only one way of expressing the strength of an interaction? To answer the DCCM question, we need one more thing: an independent measurement of the quantity represented by V over V sub c. Only then can the exponent n be tested directly. That means designing another experiment, one that does not infer the hidden variable from the same optical signal, but measures it independently. And then we return to the principle that should govern the entire investigation. We do not choose the answer. We do not protect the hypothesis. We expose it to measurement. We are not trying to prove that the universe works the way we imagine. We are designing an experiment that forces the universe to answer yes or no. And either answer would teach us something about the nature of coupling, distance, and the structure of physical reality.